Okay, recording in progress. Hide meeting controls, and this is on. Pen is live. Okay. So good morning. Happy Wednesday. I hope you are having a great week. I'm a little bit exhausted today. We had the interview of the second candidate for teaching assistant professor, and whether you know it or not, at the end of all of that, in the evening, there's a candidate dinner. So since I'm the host, I'm the one who has to do all of that stuff. And then I got back late and had to do my taxes or finish my taxes. Hopefully you got your stuff in for tax day. But that being the case, today we will hopefully finish our material on clustering and have an example in Jupyter Notebook. I decided to take a little bit different approach this year to have the practical part for each of the machine learning methods alongside the theoretical parts, and instead of kind of saving it all for the end after covering a bunch of methods. So before we begin, the usual administrative bits, the reading, I need to update. No, it has not changed. I keep forgetting the date. Yes. Um, After today, we have 5 more classes. After that, you don't ever have to hear me talk about this again. That could be good news. That could be bad news. But nonetheless, project number 6 will be out today. And this is going to concern getting you practiced with some of the machine learning methods. I'm going to use probably Friday or Monday, depending on how today goes, as a kind of workshop showing you the usage of some of these APIs in Python. We will be talking about regression after this, and also decision trees and possibly ensembles. And so project 6 will be due a week from today. I might extend it a day, plus or minus, depending. I recalculated the balance of the semester, and I like to give people 2 weeks for the final project. And so this particular project is purpose with you just using the machine learning APIs in scikit-learn. Okay, and there'll be more on that in particular on Friday's class. Okay, the final exam is, yes, question. Okay, the final exam will be on May 5th, from 10:30 to 12:30, and this is the first time in 2 years for me that I've gotten an exam period that was not 8 o'clock in the morning. So I'm happy about that as well. And so how we'll use that period is for class presentations for the final project, and the final project is the final exam. It will be a comprehensive analytics problem where you'll be asking questions as well as making recommendations based on that comprehensive analysis, which will include all the material we've covered, including the last part on the machine learning methods, the extraction of insights from the data. Any questions about that? Yes. That's the final exam period, and you'll do presentations there. And the presentations will be on what your final project implementation is, solution, issues encountered. And then the final project itself will be due the last day of finals at the close of business electronically. Um, I'm going to allow people to do groups, and we can't possibly, if all 21, 22 of you did individual projects, can't possibly fit 22 presentations in a 2-hour time slot. I like to give people about 10 minutes or so for the presentation. So that's 12 presentations, yeah, for the 2 hours. And so I'm going to have everybody record their presentations and then randomly pick groups or names out of a hat to decide who's going to physically present during that 2-hour period. Okay. All right. Any other questions? Two. I always say no more than two, for various reasons, which I won't explain here. Hmm. I use the same rubric that I do for written work as well as for project work, but certainly I'll be looking And in the assignment, I'll have a minimum specification. You must use at least this many machine learning methods. You must do at least that many visualizations. But outside of that, it's completely open-ended and your choice for what techniques and approaches you use. Any other questions? No? No questions? All right. Why don't we jump right in? Hopefully I don't forget everything I intended to do. I'm a bad example about sleep deficits. So, and I'm running a pretty big one this semester. All right, so why don't we get started? Excuse me. When we last left off, we enterprise to talk about this idea of a feature vector-based representation for your data. And I thought it helpful to throw in a type of data, image data, that we haven't talked about yet. And this is purpose with showing you another example of what I had explained before, that you're going to spend about 60% of your time dealing with the data set. For the New York taxi cab problem, we saw we're trying to understand what the recording of that data means. And the dictionaries for the data sets were very, very helpful in that. And they were published by the New York, I forgot what it's called, the Taxi and Limousine Commission. But in other cases, you're going to perform processing specialized to your data. And while the data themselves are the examples, the samples you get from some unknown distribution, you have to perform some transformation on them in order to so-called vectorize them, pose them in a vector format. And so for images, we said images, of course, have colors. And the idea with your vector-based representation for images is to describe the content of the image. And so we left off talking about color, because color is one of the descriptors of the content of an image. So we need to talk about how color is represented in a digital format. And so for that, the example we used was the RGB so-called color space. And this represented a mixture of some deepness or saturation of the three principal colors, in this case, red, green, and blue. And depending on that mixture, you get a different color. And we used the background color for a web page to demonstrate that, to jar your memories. Any questions about this? No? All right. And so continuing on with this representation of an image, we said it was a mixture of 255 levels from 0 to 255. So we of each of the basic components, red, green, and blue. And so in order to represent a picture element or pixel, which collectively define the colored dots, which are your photo, your digital photograph, we need a way or data structure to represent that. And so suppose then in your image, you have an array, two-dimensional array. You have m many rows of pixels and n many columns. It forms a matrix. But this third dimension is three cells tall. And this third dimension represents the individual contributions of the red, the green, and the blue component. These are so-called color channels or color planes. And so if you take any particular position in your image, and I'll just kind of highlight one of them, let's say this one, you'll notice there's a little column, 3 cubes tall. This is where my cartooning skills kind of try to help me. There we go. And the value, that's 8 bits, in the first slice or the first plane represents your red component. In the second slice represents your green component. And in the third slice represents your blue component. And so if we have this m by n first slice here, each one of the values in position ij in that coordinate frame is going to be the red representation of this image. It's the redness, if you will. Likewise, the next slice, or color channel, or color plane, as it's called, is going to represent the green component. And then that last one, the bottom one, is going to be the blue. And so every color that you see in a pixel array is nothing more than this particular mixture of the amount of red, green, and blue, which collectively is rendered as some color. And these are your mixture components. Does that make sense? Any questions? And so we have the red component, the green component, the blue component. And just to kind of show you an example of this, I'm going to pop over to a tool called MATLAB. And another shameless plug, if you take computer vision in the fall, you'll learn more than you ever thought you would know about this. And its purpose with analyzing imagery in order to computationally measure a notion of what the computer sees, right? So let's go into MATLAB. I'm going to stop the share and let me bring up MATLAB, and I'm going to redo the share. And we didn't really talk about MATLAB. It's a mathematical modeling environment. And so MATLAB is kind of like PyCharm, and it works with the MathWorks language called the MATLAB language. And MATLAB, or I should say Python, is very MATLAB-like. MATLAB actually predates Python. And it acts like a debugger, just like PyCharm, and it allows you to develop programs. So let me maximize that. And my interface is kind of weird. That's weird. It's just, it didn't update the, oh, that's really weird. All right, let's just roll with it. That's really, really bad. Let me do one thing. Let me do that. Minimize. Let me stop the share. Share screen again. Bring up MATLAB. There we go. It drew a little bit better. Where's MATLAB? Oops. Oh, no. Forgot to do not disturb. So you don't need to see my wife's messages. Control quit. Oh, where was I? All right. So let me. No, that didn't do it. I don't see it. Let me try one more time. Share screen. There it is. MATLAB. That looks a lot better. Okay. And so I've written a program in MATLAB that takes an image and it isolates the red plane, the green plane, and the blue plane, and then plot the histogram of intensities for the red mixtures, the green mixtures, and the blue mixtures. And so the first image I'm going to display is this image. It's a picture of a dog on a couch. And this image is 970 pixels in width. So that's along the x-axis. And it's 450 pixels in height. So it's wider than it is tall. And each location, X, Y, represents a position in the image. And when you're dealing with images, it's important to know where origin is. In some representations, it's in the lower left-hand corner. In other representations, it's in the upper left-hand corner. And so just looking at this picture, well, it seems to have kind of more reds and oranges, not so much kind of medium on the greens. And then on the blues, it doesn't seem to have very much in the image that's blue, right? So let's test this out and compute the histogram for each of the so-called color channels for this image. And then we're going to do it for another image that I'll show a little bit later. Okay, so let's go here, editor, and I'm going to go ahead and I'm going to run this. And when I run it, it's going to pop up. Let me move these controls here. It's going to pop up another figure, and let me redo the screen share so you can see the figure as well. Figure 1. Okay. Okay, so here in figure 1, along the top row, let me make this a little bigger. I don't know if you can see it. Let's see how it looks. Along the top row, we have 4 things. We have the original image, the dog on the couch, and I can zoom this whole thing. I don't remember how. With the next image just to its right, the second image, we see the red color channel. Now, your mind knows what images look like, right? You have a lot of experience with that. But everything you see that's brighter red is a higher saturation of red component in the mixture. which is closer to 255. Everything that kind of looks black in that red image, that second image, is a red component in the mixture for that pixel that is closer to 0, right? Same for the green and for the blue. And so from the original image, we said it looks like it's red. So underneath each of these images, at least up top, I have the red color channel drawn as an image, the green color channel drawn as an image, and the blue color channel. An observation is that that red color channel has very high saturations. You see a lot of redness. That green color channel is roughly in the middle, medium saturations, around 127, 100. And this blue color channel is very dark. It's closer to black in all the positions, so it has relatively low saturations. I'll direct your attention to these graphs, these histograms along the bottom. I've taken each one of those color channels and I've produced a histogram consisting of 255 bins. And if we look at this visualization, we see that the distribution of red color channel or red intensities, we have a peak here on the low side of saturations, but we have our largest peak, the mode of that distribution, on the high saturation. So this image, original image, has a lot of redness to it. Likewise, the green component for the mixture, we see it's roughly around the middle. That's where we see the largest peaks in that histogram, representing the intensities or the size of the green components in the mixture of red, green, and blue. And then lastly, in the blue, just like we saw from the image, our peak in terms of the intensities is very, very low saturation, closer to 0. Right? Does that make sense? And so when you see an image, the teasing apart of the distributions of the components for the red channel, the green channel, and the blue channel is a great representation of the color content of the original image. And so when we first talked about describing the image, we saw a picture of a building and we saw a picture of a sunflower field, I should say. And the question was, how do you describe the content of these images? Well, one way you describe the content is by the mixture of colors across the image, and you can use the distributions over the red, green, and blue channels in order to do that. Does that make sense? Any questions? And so this is an example of turning your data set into a vector representation, and later we'll actually see how you do this with the color portion that you use to describe the content of images. Okay, so let me stop the share. And I'm going to minimize that, get rid of that, and let's go back to PowerPoint. And PowerPoint is kind of wonky, so I always have to save it and then restart the share. PowerPoint, share, and let's slideshow. And then full screen. Hopefully that is showing up properly on the recording. Let me just let me do one thing. Is PowerPoint full screen? Okay, all right, good, thank you. All right, so we have our images, and we said that one way of describing the content is the color distribution over all the pixels, looking at the intensities of the red, the green, and the blue saturations. Why didn't my slides? So if we take our histograms, and in the case of this visualization, imagine instead of 255 bins per histogram, we had 10 bins per histogram. So we can turn the color representation or color content into a vector-based representation by literally collecting the bin counts for each of those bins across our histograms for the red channel, the green channel, and the blue channel. So in this case, for the building image, we know the colors are different from the sunflower field image. So then we take the 30 bins, 10 each of red, green, and blue for the respective histograms, and then we concatenate them to make 30 vectors. And that 30 vector for the building is going to represent the building content. in 30 dimensions. And that 30 vector from the sunflower field is going to represent that picture of the sunflower field in 30 dimensions. Does that make sense? So this is an example of higher dimensionality, and it's very typical in real data sets for your vector representation to be in the tens, hundreds, and many times the thousands of dimensions. Okay. So also, we can extract the edges. And I won't go into those techniques. I'll defer you to take the computer vision course. But an edge represents an abrupt change in intensity. And you can digitally compute the derivative of the intensity in X and Y and characterize the edges in the image. Another thing we talked about was that in this building image, you have a lot of edges that are 180 degrees and 90 degrees. So if you then took that representation of all the edges in the image and produced a histogram, you're going to get two peaks or modes, one over 180 degrees and one over 90 degrees. We said that the sunflower picture, nature prefers curved things. If you see a square flower or a square tree, that's quite odd. But if you compute the histogram for edges in images of natural objects, because they tend to be curved, oftentimes round, you're going to get edges that are at many orientations close to uniform across 0 degrees to 90 degrees. And so the edges in the sunflower picture are going to be different from the distribution of the edges in the building picture. So again, we can take a histogram representing the distributions of edges in your images. And if we had 10 bins, we can use those as so-called shape features. Shape is a measurement of all of the edge content in your image data. And so we take our color features and we concatenate those color feature vectors from the color distribution with the edge distribution. And appearance is nothing more than the combination in some form of both color and shape. Okay. Any questions about this? Does that make sense? Yeah. And so why would we do this? Okay. And because I can only represent things on the screen well in 2 dimensions, let's imagine we had 2 features. One feature represented color and one feature represented shape. Now, in one case, we could plot in multiple dimensions, and you could imagine in 40 dimensions plotting a point representing that example of the building image in its vector format. And you could imagine in 40 dimensions plotting that point representing that particular sunflower image in 40 dimensions. But I'm only plotting it here in 2 dimensions because I can't plot 40 dimensions on the screen. Does that make sense? Any questions? And so as a so-called feature vector, the projection of each of these vectors, for example, we take the X component or horizontal component of that point for the building image, and that's going to represent the color value for that building. And if we take the Y projection of that point for the building, that's going to represent the shape feature for that building. And so whether we have 2 dimensions or 40 dimensions, the projection of that point in feature space onto each axis is going to represent that particular aspect of the feature, be that a color feature or a shape feature. Does that make sense? And so now, why do we do this? Why do we represent things as points? We started out talking about this idea of birds of a feather flock together. It's a nice, catchy little phrase. But if you want to answer the question of how similar is the content between these 2 images, now we can make use of vector operations like the Euclidean distance between these points in space to tell us how similar the content is. And it kind of makes sense. If a point is very close by, let's say we had a point x3, let me draw it on the tablet. Let's imagine we had a point, and let's call that point x3. And let's imagine x3, it's a vector, x3, and let's imagine it was really close to x1. Because it's close to x1, that means its shape feature is going to be close to x1's shape feature, and its color feature is going to be very close to x1's color feature. And so because of that closeness in each one of the features for X3, the closeness to the features respectively for X1, that means it's going to have very similar content. Its color is going to be close to its color, and X3's shape is going to be close to X1's shape measurement. Does that make sense? Any questions? All right. And so using Euclidean distance, and that's not the only distance measure out there, it's just the one I talk about in this class. What this tells you, this distance, is how similar or how dissimilar the content is between these two images. Does that make sense? So you have your vector space representation, and now you can make use of all sorts of distance measures to tell you how similar they are or how dissimilar they are. And this is the basis for grouping together these images based on the content. Okay. And so why is this useful? So I thought I'd tell a story. Back when I was a kid, and also through high school, film was the primary modality for how you took pictures. And I remember, when you bought film, you'd kind of have to know what speed of the film you needed. A higher speed could capture faster moving objects. And that cost about between $5 and $10, depending on where you got it. And then once you took your pictures, you'd go and develop it, usually at a drugstore, and it would come back in 1 or 2 weeks, and you'd get your negatives as well as your prints. And so from there, you'd look through your photos, and then you'd get a bunch of photo albums, these books in which you kind of store the images you like and build these collections of photo albums. And you'd save the negatives. And if you wanted to give someone a copy of the picture, you'd go and get that picture reprinted from the negative and then pay for it and then mail it to or give it to whomever you wanted to give it to. Now, I remember I used to carry around a camera quite a bit. I was a fan of photography since elementary school. And you'd kind of hold your shots because that process was expensive and it was time consuming, right? But I remember when they started putting out digital cameras, and I was an early adopter of digital cameras, and it made it much cheaper and you were more likely to take more shots. And I'll never forget when they put a digital camera for the first time in a cell phone. And I remember thinking at the time, I was in grad school, that's the silliest idea I've ever heard of, right? Because you have a real camera with all the different features, you can adjust the exposure, do all sorts of interesting stuff. Now, by today's standards, these camera phones have gotten quite capable. But what did this allow? Well, it meant people were very generous with the shots they took. People were taking photos, sometimes a little too much, but taking photos all over the place, all the time. Now, it's very typical for an amateur photographer to accumulate a photo library, these images, labeling in the tens of thousands and sometimes hundreds of thousands of photos, right? Been taking digital photos for any amount of time, those libraries are going to get pretty big, okay? And so this idea of analyzing image content through this idea of grouping using distance measures and feature space is useful for automating the decision about like kind. So let's imagine in this digital photography example, you have a huge library of photos and you want to organize them, right? You want to put all the vacation photos with all of the tree photos and so forth. So you run this thing called clustering, a form of unsupervised learning, which evaluates just the feature values, namely in this case, the content of the images expressed through these feature vectors. And it arrives upon groupings or associations between these like kinds. Now, of course, within each grouping, here we have pugs on the left, we have yellow labs on the upper right, we have German Shepherds, dogs on the lower right. Yes, there's some variability within each grouping, but there's some similarity in the content, both in terms of the color as well as the shape, the edge orientations. And so this is very useful. And when you automate this grouping, once the computation halts and it says these are the images based on the representation and their content, these are the ones that are most similar to one another, you go in to your grouping software and you give it a name, right? The computer doesn't know what they are. All it knows is that these feature vectors are closest to one another. And so it's going to assume, because the content is similar, that they belong together. This idea of birds of a feather flock together. And so after the fact, once this grouping is done among your tens of thousands of images, you go back in and you analyze what these final groupings are. And you might change the membership of some. It makes some errors. But you go in and also give it names, right? You do some analysis. And so this is all about the clustering process. It's the comparing of data items based on their similarity. And you're going to spend time trying to figure out methods for representing these quantities as feature vectors. And there are some other decisions that you have to make that we'll talk about in a few slides. Question? The RGB content determines what the clustering is, because when you convert it to a vector representation, each point represents some histogram, the distribution among the reds, greens, blues, and the edge orientations. And so this Cartesian distance, that's the operator you use to say this particular set of content, how similar it is to that particular type of content. So there are two things that are impacting. It's the distance measure you use, and there's many different ones that we don't have time to talk about in this class, but there's also the representation. Because if you change it, for example, from, say, 30 bins of color, 10 red, 10 green, 10 blue, 10 for shape, maybe you change it to 5, 5, 5, and 10, right? So that would be 25 features. The point cloud is going to look different because the representation is different. And so the representation is going to impact ultimately what the distance measure is going to measure, but then the distance measure itself is also going to impact what is considered more similar or less similar. So it's both of them. Okay. Any other questions? Does that make sense? Yeah? All right. So when you have these groupings, you give it a name. And giving it a name is part of your analysis. You analyze these clusters. You can also compute things like the summary statistics, and you can also do things like run max likelihood estimation or method of moments estimation, and then get a distribution. And now with that distribution, you can sample from it and produce artificial data, like artificial images. Okay, does that make sense? Any questions? And so let's take a look at the so-called clustering task. And going back to the credit approval problem, you have two features representing each customer. And this vector representation is computed by taking information from the mortgage application, okay? So just like we saw for the image had histogram, bins, counts representing colors. Here, our vectorized representation of a customer is that data that you use to represent them from the mortgage application. So we have our historical data from the bank, our so-called in-sample data, and we process it in vector valued form, keeping in mind that each vector instantiation, each row of this table representing each customer, is thought of as a joint probability over a set of random variables where each random variable's value is a feature. And so here we have the salary feature and we have the years in residence feature. And this is a two-dimensional vector because there are two variables in this particular example. Does that make sense? Any questions? No? All right. And so we have a data set, and in this unsupervised learning model, we don't know what their labels are, right? If you have labels, that's supervised learning, the ground truth labels by the unknown target function, but this is unsupervised. And we said in the unsupervised learning case, because you don't have the supervision signal, those ground truth labels, the only thing that you're left with is analyzing something about the features. And that analysis is this distance measure, this comparison of how close they are to one another. So we have our points in D dimensions, and across our entire data set of size n, so n many customers in our historical data, this is going to be plotted in your feature space, and it gives us a point cloud. Okay, that hasn't changed. Now we take each one of these points and we compare them distance-wise using their feature values. Okay, so we enterprise to group them together, just like we said in that image library example. And once we get our groups, we identify the members of each group, and now we analyze the groups. So you compute things like the summary statistics. You might fit a distribution, knowing what those values are. In this case, salary is real valued. So that's well represented by a normal distribution. Years in residence, that's time, that's real valued. So you could represent time either as an exponential distribution, or you could represent it as a normal distribution if you chose to. Okay, so you can perform all sorts of analyses on these groupings and do lots and lots of wonderful things with them. And one of the things in our analysis is to go in and you give them names. Now, in this case, it's on purpose. I've made two groupings. And you might call one grouping, after you analyze it, the mean salary, the mean years in residence for each grouping. You might call one of them those who you're going to approve and those who you're going to deny. So using this idea of grouping, you can go in after the fact and say, everybody, I don't have labels, but everybody in this grouping, I'm going to assign a label of deny, or in another grouping, I'm going to assign that plus label of approve. So then you can go through and you say, everyone here is going to label of +1, and everyone in this grouping is going to have a label of -1. So you can use this clustering to assign labels in the absence of knowing what these ground truth labels are. And you treat them as ground truth, and then you can run these through perceptron learning and then have a predictor that can accept a new customer that has not yet been seen. And now you can predict whether that person should be approved or denied. Does that make sense? Okay. Any questions? So we haven't talked about a lot of things. We haven't talked about the grouping, call them denials and approvals. And we haven't talked about the algorithm for how you find this best grouping. So that's coming. But any questions so far? No? All right. And so let's jump in to so-called k-means clustering. And clustering is a very popular method. And k-means is just one way of doing that. There's k-medioid, there's kernel k-means, there's dozens and dozens and dozens. But I'm just going to give you the basic framework and leave it up to you to consult the literature for all sorts of variations of the primary algorithm. And you can also change the distance measures to like dozens of different things. And these distance measures are good for certain pathological considerations for your data set. All right. So k-means algorithm, if you look, k-means clustering, if you look in the literature, you'll see Loyd's algorithm pop up a lot, and Loyd's algorithm is the main algorithm for it. And so it starts out with a parameter k that you define. You make a priori the assumption that I want to know what the data points should be if I want 2 groups, or if I want 3 groups, if I want 10 groups. And Loyd's algorithm, when it converges or halts or completes running, it's going to give you those groupings based on that k value that you had. Now, later, when we talk about cluster quality evaluation, we'll talk about how you select the best k. But for now, let's imagine k is the number of groupings you desire this Loyd's algorithm to give you. Okay. Does that make sense? All right. Now, every cluster has what's called a center. And that center represents, just as the name implies, the middle of that grouping. And so here we have 2 groupings. One grouping we've called the denials. That's our label, our name. The other grouping we've called the approvals. Now, if we were to take the average of all of the salaries in the first group and the average of all the years in residence, the sample mean, we're going to get some value center that we can plot. That's called mu1 for the first group. This is group 1. And we would call that mu2 for the second grouping. And so what these cluster centers represent is the notional middle in feature space among all of the points that belong to our respective groupings. Does that make sense? Any questions? No? All right. So here in Loyd's algorithm, we start out with some value k, which is the number of groupings. And if we have k groupings, we're going to have k centers. But in the beginning, we don't know what those centers are. So how do we set them? Well, we just randomly create them. So you randomly select a salary component for mu1, randomly select the years in residence component for mu1. For mu2, you randomly select a salary and a years in residence. Is it correct? No, it's not, because it's a random number you've inserted, but you have to start somewhere with your initialization. And what Loyd's algorithm does is it fixes them up. And we'll show exactly how it fixes up those centers. The next thing we need, now that we have the centers for the K groupings for some K that you specify, you want Loyd's algorithm to produce, you then need to put the points into clusters, okay? And so in this version of Loyd's algorithm, for the ith grouping, we refer to it as S sub I. So S sub I is going to be a set, and in that set is going to have some vectors in it, which are the points that go in that particular cluster. So maybe X sub K is there. No, that's a bad choice. X sub T plus 1 is there. Maybe X sub T plus 7 is there, right? So if we have K groupings, for K assumed clusters, we're going to have the first grouping, S1, second grouping, S2, up to and including the kth grouping. Okay. Now, each one of these groupings is a set, and each set is a collection of these points. Together, your entire data set and many points is going to be placed somehow in those K-many groups. Does that make sense? Okay. So now, in order to start this algorithm, we just said we randomly select these centers. Okay. Now we're going to randomly select the assignment of our data points to the clusters. So how do we do that? Okay. Well, we have our first data point, our second data point, up to and including our nth data point. Each one of these are vector valued in D dimensions, so 2-dimensional, 3-dimensional. In the case of the mortgage approval, it's 2-dimensional because we have a salary feature and we have a years in residence feature. And then we can think of these clusters, these sets, S1, S2, as sort of these bins, and we have K-many of these bins. So now we iterate through each one of our data points. We take the first data point, and you can imagine you're going to flip a K-sided die. If that K-sided die comes up 1, we're going to place that in the first grouping, in the first set. Let's say for the second one, it came up 3. We're going to place that in the third grouping. And so we loop through each one of our in-sample points, and we select at random a number 1 through K inclusive, and that number is going to be the assignment of those points to these groupings. Does that make sense? Any questions? So if we think about it, all right, we have K choices to assign the first point, times K choices to assign the second point, up to and including K choices for the nth point. And so if we look at that, we have a total of K to the n power. That's all of the possible assignments you can have of points to clusters. But you're just picking one of them because you want to make that initial choice. Does that make sense? Any questions? Now, at the beginning, this is a lousy grouping. It's all randomized. It doesn't consider anything about the feature values and similarity. But at least now we have a starting point. Okay. So the next thing we're going to do, we're going to minimize this expression. And let's go back to what we said before, is that we have a possible K to the n power, different assignments that we can have of points to clusters. So that's exponential in the number of points. And we can't solve for that precisely because there are just too many of them. If n was 1,000,000 points and K, the clustering, was 2, that would be 2 to the million power, right? So that doesn't scale well. We have to find some way to do good enough in our fix-up of this. So we're going to minimize the following expression. And what this following expression looks at is it has the square of the Euclidean distance between each point in a cluster and the center of that cluster. So that's the center, and that's each point within that cluster. On the inner summation, here we have xn within cluster K. So each of the points xn within that particular grouping, and this is going to be our S sub k. So our xn is going to be all of the points within that grouping we're calling cluster K. In the beginning, it's randomly assigned, but that's okay. We can improve upon this over time. Does that make sense? Any questions? So now this outer summation, that says for every single cluster. We don't just have a particular cluster, we have all of the clusters from SK down to S1. Does that make sense? Now, if we wanted to find the assignments of points to cluster that minimize this expression, you could, in a brute force way, meaning just without any sort of elegance about it, search through all of the possible k to the n assignments, execute this function, code it up and execute it, and then choose the assignment that minimizes that expression. But again, because it's exponential in the number of points, that's not going to end anytime soon, right? It's intractable. So what does this Loyd algorithm do? It finds a local minima, and this is the objective function, and it does it by alternating between two steps called the expectation step and the maximization step. So at this juncture, we have k centers, and we have an assignment of those endpoints to those k groupings, albeit a non-optimal or a very poor assignment. We start out by updating the centers. When we do this update, it sets the centers mu1 through mu k precisely to the center of the points that were assigned to that grouping. So now this set of centers, thank you, becomes more realistic. It reflects the assignment that was done of points to clusters or groupings at the beginning. Okay, any questions? No? All right. And so now that you update the centers, you say, okay, my centers are real now. Let me fix my centers. I'm not going to change them. So you update the centers, and then you fix them. Meaning you don't change them. You keep them constant. And once you fix them, after you've updated them, you now reassign your points to the clusters associated with the updated centers. And so how do you do that? You line up all your points, x1, x2, up to xn. They're all vector valued. And now that you've updated the centers, you have the first cluster, S1, and it's associated with the center mu1. You have S2, your second cluster. It has a center mu2. And you also have up through and including SK, your kth grouping cluster, and it has a center mu k. Now at this juncture, because we calculated the mu's, the centers, and fixed them, now we take our points again, we iterate through the points, but now instead of assigning them randomly, we're going to assign them to the cluster or the grouping S who has the closest center. So we're going to compare all the features of X1 to mu1, mu2, mu3, up through mu k. And let's say X1 was closest to mu2. We're going to say, aha, you're closest to that center. X1 belongs in the second grouping. Going to go to X2. Say, wait, you're closest to mu k, that center. So X2 is going to go in that kth grouping. Does that make sense? Any questions? Now you do this comparison based on Euclidean distance. Props up again in feature space. So it's the distance between points. So now that you've reassigned your points to the closest center, well, that means the grouping changes from what you first assigned it to. So what do? You go back to, now that your grouping has changed, grouping changed, you go back to that first step. Now that the grouping has changed, because you've conceivably reassigned the points to different groupings, you then recalculate the centers, because the center is going to change. And so you alternate between this updating the center and regrouping based on proximity to the updated center. And you go back and forth in alternating fashion. And so this second step, that's called the maximization step, because you are optimizing or minimizing, minimization, maximization are the same thing. you're reassigning them based on minimum distance to the center. And this is the expectation. This is the mean or the average center now that you've reassigned the points. Does that make sense? And so you keep doing this alternation until one of two things happens. It converges. That means the points no longer change their grouping. And what happens when they no longer change their grouping? The center remains the same. If you recalculate the center and nobody's changed groups, the center mu sub k for each one of the groups is going to remain fixed. It doesn't change. Or some number of iterations of this alternation is achieved. So you run it for, say, 10,000 steps or 1,000 steps, and either the 1,000 steps is reached, this alternation between the expectation and maximization step, or the centers don't change, which is the same as the groupings don't change, and you halt when you detect that. Does that make sense? Any questions? Now, this is an approximation. It'll give you a local minimum, but it's not going to give you the global minimum because there's an exponential number of assignments that you'd have to try. So oftentimes in the APIs for Loyd's algorithm or k-means clustering, it has this parameter called number of restarts. So it'll try that algorithm maybe 10 times or some number you specify, and it'll take the best one. Okay. Any questions? Does that make sense? So now that you have this grouping, of course, there are many other considerations. Okay. How did your algorithm perform? What did the groupings look like? Mind you, you can visualize the groupings 2 or 3 features at a time because you can only display 2 or 3 axes on the screen when you visualize. And a good way to visualize it is a scatter plot because that scatter plot allows you to compare the variables in question that you're displaying on the screen. So what were your clusters? What name would you assign these clusterings? It's up to you. How did the performance change if you modified the parameters? If you change the feature vector, if you change the number of clusters, if you change the distance measure. Somewhere among these choices is the notional best choice, and that's entirely dependent on your application, what you're after. Does that make sense? So you could choose a distance measure, a number of rounds, a feature representation, such that your distributions have smallest variance for each of the groupings. Or maybe you want the ones that have the least skewed distributions among the groupings for some quantity. It's entirely up to you, but now you have these analytical tools that can say, show me what belongs together, and now I'll apply my analyses in order to measure what good desirable qualities I need out of the associations that I find between data points. Does that make sense? Any questions? No? All right. What are the summary statistics? And can you model these distributions formed by the clusters? That's where max likelihood and method of moments estimation comes in, because now if you can model these distributions, knowing what you know, you can sample from them and now produce artificial data or fill in the appropriate missing values if there's a missing value from a new measurement. Does that make sense? Any questions? No? All right. So all of the pain I put you through all semester is for a reason. All right, so let's take a look at this group membership. These groupings are defined by the cluster center, as we said. Yes, we give them names, but algorithmically, you refer to it as the first grouping, the second grouping, the third grouping, and so forth. And so they're defined, these groupings, by the cluster center. So in this case, for the mortgage application problem, we had 2-dimensional feature space. So we take the sample mean of the salary feature, and we take the sample mean of the years in residence, and this is going to give us our mu values, defining our centers. And so these centers are a proxy for how you name these clusters. Now, of course, by now you know, depending on the characteristics of the distribution, sample mean might be a lousy way to represent the center. So there's all sorts of things like using the median, and there's a different version of Loyd's algorithm. Instead of k-means clustering, it's called k-medioid clustering. And a medioid is a center that you choose from among the data points themselves. All sorts of variations of this. And so we can have a cluster center for the first grouping, likewise a cluster center for the second grouping. And in the case of using the mean for the center, we just literally take the sample mean of each one of the feature axes among all of our measurements for each grouping. Does that make sense? Any questions? No? All right. And so now, how do you use this? Okay, let's imagine a new individual comes along in the bank. We decide the membership of this new individual. First, we convert that new individual to the same two-dimensional vector. And then we take the distance between each one of the cluster centers and this new individual. And whichever distance to a center is closest, in this case, that new customer, the yellow dot, is closest to mu1, we say, aha, you belong to this cluster S1. And that cluster we called the denials. Now, you could certainly go into the group of denials and maybe chop it up into quartiles and say, among those who are the denials, if you are in the 75th quartile or above, we're going to have the special mortgage program for people maybe who don't meet the same income standards for what approval means. So you could do all sorts of things within the grouping using things that you know already. Does that make sense? Any questions? No? All right. And so what can you do with this stuff? Lots of very cool things you can do. Recommendation is one of them. Have you ever gone on Amazon and it said, if you like this, you might be interested in that? That's just an application of clustering. Okay. So we have our data. We've clustered it. We've analyzed it. We've called one of the groupings in this clustering of into two groups, the denials on the lower right, your lower left. In your mind, you kind of invert left and right because you're on that side of me and reverses. But on your lower left, you see the denials. On the upper right, you see the approvals. So you do that clustering. So now you have a new point in feature space. You register it, and you know that it belongs to that denials grouping. Okay. So now you determine the group membership by taking the distance between that vector version of that new point in feature space and the groups. Now, this new person is converted into a feature vector. And let's imagine you knew the salary for this person, but you didn't know the years in residence. So you project this point along the salary axis and you say, okay, which group does this person belong to based on the salary? So what do? You take your interquartile range, and you go 1.5 interquartile ranges above the median, below the median, and you determine, does this person belong to the denials group or to the approvals group? Once you know they belong to the denials group, you could do it that way. Okay. Now you use max likelihood estimation for the years in residence feature for that grouping, and then you sample from it and you use that sample to fill in that missing value for that years in residence feature for that new customer. So you can use it for structured data, these groupings, to appropriately fill in a missing value. And the reason why doing it this way using clustering is because if you have two subgroups, there's different averages and different variances for the salary for the denials group versus the approvals group. So you can, with more specificity, fill in these missing values instead of just substituting a sample or mean from the entire data set, because this data set is structured. It's two subgroups. Does that make sense? Any questions? No? All right. Likewise, imagine you're at a large streaming service. I won't mention names unless they want to donate money to the department. And they characterize movies based on genre, and genre, let's say, is measured based on the percentage of certain types of content. So let's imagine you have the comedy axis, which is what percentage of that movie is representing comedy. And you have the action axis, which is measuring the percentage of that movie considered action. So let's say you have these movies described based on comedy and action, and these aren't the only ways of measuring it. You have one grouping you call sci-fi, and you have another grouping you call the action comedy, which is a type of genre, I've been told. So you plot these movies in feature space, and you come up with groupings, come in, look at the groupings, and you give them names, sci-fi and action comedy. So then you come along, you log in, and you pick a movie. Okay, well, You characterize this movie that you picked based on these two measures, percentage comedy and percentage action, and you take the distance between this movie you've selected and the centers of these two groupings. Okay. So now, once you've determined this group membership, um, you can now take the features and put a little distribution over that particular percentage action and percentage comedy for that new movie. And now you can make a recommendation by sampling from these distributions. So you take a normal distribution and you center it, its mean, over the action content for the features for that new movie you've selected. Do the same thing for comedy. And then your recommendation, you might like this, if you like that, is just this sort of wiggling, if you will, some amount above or below this movie you've selected for each one of these characterizations. Does that make sense? Now you could do it above and below, some place near the movie you've chosen, or you could sample within that entire grouping for something even more different, but within that category. Does that make sense? And so now, if you made the variance of these normal distributions even bigger, you can kind of ooze out into other genres and select something even more different from what you were interested in. Does that make sense? And so you can use this idea of max likelihood estimation to fit the distributions. You can use locating this distribution by changing the mean, and then you can use the sampling once you know these distributions to recommend new content that is similar or a little bit different from what you've chosen. Does that make sense? And this happens in custom couponing, right? You go to the store, you buy something, it's a market basket, you buy one thing and all of a sudden it has coupons like, wow, how did they know? It's just another application of clustering. You could make a whole career off of just clustering and the umpteen many variations involved in clustering. Does that make sense? Any questions? All right. And so how do you choose this K? That's sort of the proverbial elephant in the room, right? How do we know how many clusters is a good amount of clusters? I'm glad you asked. Oh, you didn't ask, but we have some number of clusters, K, and we said K is the number of groupings you desire when Loyd's algorithm halts, okay? So K can be any number. K can vary from 1, which is trivially true, one cluster, everything's together and among your data, up to n clusters, where each cluster on the other boundary value only has a single data point, okay? Well, we'll kind of throw out those from consideration because it doesn't make a very interesting distribution if you only have one data point per cluster, okay? So how many clusters K? There are two criteria for what makes a good clustering. The points within a cluster, if they're very closely bunched around the center, that's a very compact cluster. It means there's very little variability in the data points within each grouping. So a compactness is one of the criteria for what makes a good cluster. Let's look at this measurement of compactness. And so here we have each cluster, the ith cluster, S sub I, the ith grouping. For the ith grouping, we know how many points are in that cluster. That's the TI. And so TI says how many points are in this grouping, okay? So if we say 1 upon TI, that's kind of a uniform probability that treats each point within a grouping as having equal probability. And so just like we talked about with moments, the force times the distance from the center, we're going to compute the qth moment for all of the points within the cluster. And so A sub I, that's the cluster center. And, you know, depending on what you look at, the notation is going to change. So we take the difference, the distance between each point in the cluster and the cluster center. We take the magnitude. We care about the distance, but not if it's on the negative side or the positive side. We exponentiate that to some value Q. We sum together those exponentiated differences, and then we take the root of that. No, I show it this way because what I showed you with the L2 norm, that's just the square, Q is 2, and we take the square root of that sum of squared differences. Does that make sense? So in the general framework, you can use whatever Q value you want, but the Euclidean case, Q is 2. All right, so That compactness measure takes the sum squared differences among all of the points in each cluster, and there's one for each cluster. So that is the intra-cluster distance, how clumped together, close they are, tightly packed around the center. Does that make sense? Any questions? No? All right. So then a good clustering, not only is it compact for all the points in the groupings are very spread far apart from one another. So they're very well separated. And so well separated, you're just measuring the Cartesian or Euclidean distance between all of the centers among the K mini clusters. Does that make sense? Okay. And so here we have n dimensions in this notation, and we have the ith cluster. So you have an ith cluster, and you have a jth cluster. And here's I, the ith cluster, and here's a jth cluster. If this is in 2 dimensions, n is going to equal to 2. Okay? So we say, what is the moment, or the difference rather, squared difference, between the salary feature of the ith and the jth cluster center, and then what is the squared difference between, for example, the years and residence feature between the ith and the jth cluster center. So we add all of those exponentiated differences, and we take the root of that. Does that make sense? Okay. And in the Euclidean case, p is equal to 2. So it's just nothing more than the square difference, or the distance rather, between the ith cluster center and the jth cluster center. Okay, and so for that, we get this m quantity in the notation, and we do that for all of the clusters that we have. We have these dispersion or these separation values. And so now we talk about the cluster similarity. We mix together a proportion of 2 things, the sum of the compactness for the ith and the jth cluster, and we divide that by the dispersion or the separation between the ith and the jth cluster. That's going to be our Rij value. Does that make sense? Okay. So now we have this ratio, and if the compactness is very small, the numerator is going to be very small, and therefore this quantity is going to be smaller. If the dispersion is really large, the denominator is going to be large, and this Rij quantity is going to be smaller. And so we want the 2 together very compact and very dispersed. So we want the numerator to be small, and at the same time, the denominator to be large. And that's like this case. They're very compact and very spread apart. Something that would violate that, we'd have something that's much bigger, and they're very close to one another. This would be one center, that would be the other center. So we want this R value to be small. That represents the best of what we want out of our clustering. Does that make sense? Any questions? No? And so for any particular cluster, there's going to be some other cluster different from itself that is the closest to it and also the most dispersed, right? And that's going to be this Ri value. So Ri is for a single ith cluster, and what it's saying is what is the j that violates this, has the worst value for this proportion. And you can think of that Ri value as this idea of the cluster distance, right? In the worst case, how similar is some other cluster to you? Does that make sense? Any questions? All right. So with all of that, something called the Davies Bouldin Index, these are the last names of the folks who created this, is the average cluster distance. And that Davies Bouldin Index, we want to minimize it. And that minimization happens at the K value, or the number of groupings, where this particular statistic reaches its smallest value. Does that make sense? So it's the smallest, the K, that engenders the smallest cluster distance. Okay, so let's take a look, and I'll end there in the next 4 minutes. Stop the share, and I'll probably end in this in the Jupyter notebook. Where did it go? Here we go. So here's the Jupyter notebook, and I'll post this on the Moodle site. And so I've done the usual imports, the pandas, because I'm going to use data frames, some plotting, and NumPy. And then from scikit-learn, sklearn clustering module, I'm going to import the k-means clustering library or module program. And then from scikit-learn.metrics, all sorts of useful measurements, the Davies Bouldin score, which we just talked about, which is the worst case for this ratio of the compactness for the two for clusters divided by the dispersion. And so I'm going to take a data file called historical customer data. And this is an example of the mortgage approval example. So we have the default index, we have years in residence as a real value, and we have annual salary. And in this case, throw in the ground truth target labels. But I'm not going to use the ground truth target labels. I'm just going to throw them away and pretend I didn't have access to that. But the reason for including them is so that I can plot them and show you what the ground truth is, and then show you how close to the ground truth that clustering actually gets. Does that make sense? All right. And so I know that I have 200 positive examples, 200 negative examples because I created the data set. I extract the data only. So I only take years in residence and annual salary. And you can see I don't have the target labels there. So this is an instance of an unsupervised learning program problem, an unsupervised learning problem. The caffeine's wearing off. So then I take my positive examples and my negative examples, those that I know ground truth to be +1 approvals, and those that I know ground truth to be -1, and I go ahead and I plot them, positive and negative examples, with my ground truth. The positive examples are the red pluses. The negative examples are the blue X's. And I think I use X's because I didn't know how to say blue minus sign. I have to figure that out later. But as you can see, feature space, I get these point clouds. And now I'm going to plot the unsupervised learning version. And I plot them both in green because at this juncture, you don't have the labels. You don't know which are positive and negative examples. So I don't color them that way. Uh-oh. Did I not share? Oh, share screen. No, I did not. Okay, why did that go away? All right. So I don't color them because we don't have the labels, right? So you see the point clouds knowing the ground truth here, and you see the point clouds not knowing the ground truth labels there. Okay. So now let's go ahead and I'm gonna I just lost my place. Why did I do that? Okay, all right, I minimized it. So I'm gonna run k-means clustering, and instead of saying two groups, because conceivably I wouldn't know that it's two groups, approval and denial, I'm gonna say cluster it into three groups. Okay. Now when I call k-means on the NumPy array representing the data only portion, I give it the number of clusters, and there are other things you can specify like the distance measure and the number of restarts and things like that. If I look at the labels attribute, every place it's the 0th cluster, first cluster, or second cluster, it starts the cluster numbers S starting from 0. So I have three clusters, S0, S1, and S2, and position by position, here, the 0th data point, it said, is in cluster S1. This data point, it says it's in cluster S0. And the other data point here, it says it's in cluster S1. And so the thing to remember here is when it gives you the clusters, it doesn't say the first cluster, the second cluster, the third cluster, like the math written down in publications would say. It starts it from 0. So that's important to remember. And each position in the array reflects the position or the row from the data table, and that particular vector instantiation, that individual, is in the cluster, which is the number in that position. Does that make sense? Any questions? No? All right. So now, knowing that, I go ahead and I slice out of my data those particular vectors based on the cluster labels. So I extract those with cluster label 1, cluster label 0, cluster label 2, and I call them group 1, 2, and 3 respectively. So now that I have the data, I'm going to go ahead now and color my data based on the cluster group membership. So I go ahead, I execute that, and you can see here, I have my blue cloud, right? I have my plus cloud, and then I have my purple cloud remaining. And so let me go ahead in this next one. I start with 2 clusters and end with 8 clusters, and I run my Davies Bouldin score on the k-means clustering from each of them. And then I plot my Davies Bouldin score, and I see my best clustering is at the minimum of this DBI score. And so I do DBI score for 2, for 3, for 4, for 5, etc., within some range of k values. And wherever I get the minimum of this graph, in this case 2, that's going to be my best clustering. And that's how you choose the optimal K that you report. No, I know it's 2, but I'm going to be stubborn and say what happens if I want to do clustering of 4. Okay, I go ahead, I extract them, and then I plot them as 4 different groupings. And these are the 4 groupings that I get. And so this idea of grouping is immensely useful. You analyze the clusters, you give them names, and you can use it for recommendation, for intelligent filtering and substituting for not a number values, all sorts of wonderful things. But you choose the K value based on the minimum of the DBI score. And that's not the only cluster quality measure that's out there, but it's a very popular one. Any questions? That makes sense? Yes. For DBI, it's metrics on scikit-learn, scikit-learn, sklearn metrics. And there are many, many other types of cluster metrics out there. Any other questions? No? So you choose the clustering, you perform the clustering, you extract or segregate the data points based on the memberships from clustering, and then you do the analyses on the resulting subgroups of points. So I'm about 2 minutes over, apologize. We'll end there, and I will see you all on Friday. Have a great rest of your week.